Today what we will do, we'll discuss some of the properties of the continuous time Fourier transform. So what are those? Fourier transform is linear. A shift in the time domain results in multiplication by an exponential in the frequency domain. Shift in the frequency domain results in multiplication by an exponential in the time domain. Time scaling results in omega replaced by omega by scaling factor. Reversal in time results in reversal in frequency. So as I told, I'm not going into much details. Yeah, then there is this duality. Okay. If at all you have, you can see here, this capital X has been written here and a small x has been written here. That means if at all I have some x of t, who's got a Fourier transform 2 pi into x of omega. X of t has got a Fourier transform x of omega, and you have been given a equation of x of t where your omega has been replaced by t, then your answer can be same as what x of t would have been in the frequency domain with t replaced by minus omega along with the constant. Okay, still it is confusing, we'll see that. Yeah, then one more thing, the moment you see an omega getting multiplied in the frequency domain, it is time to differentiate in the time domain. The moment you see a t getting multiplied in the time domain, it's time to differentiate in the frequency domain. You can see you divide both the terms by minus j, you will get a j here. Okay. Then this is spooky property, we'll see that when the time comes. Then convolution becomes multiplication here also, even it was there in Laplace. Okay, multiplication becomes convolution, this also follows from the duality only with the 2 pi. Then there is this Parseval's theorem. As I told you, Parseval's theorem is for, usually its application is in finding the energy. Okay, its application is in finding the energy. Okay. So let us see what all sorts of uh, problems we are looking at here. So what we will do now, we will see the problems on each of this. So here is a list of the properties. Anyway, we've seen this. Let us straight away go to the problems here. Okay. So the first problem what we have is the usual suspect. Okay. Finding the inverse DTFT. And here what we will do, unnecessarily we will not get into calculating using the expression. Rather what we will do, we will apply the partial fraction expansion. Okay. You would be lucky if at all you get these kind of problems in the exam. Okay. So you can see here you will substitute for j omega. You do not substitute for omega alone. Okay, you substitute for j omega together based on your requirements. Okay, so this is very similar to what we did in the previous in DTFT or in Z transform. In DTFT, we substituted for, what did we do? We substituted for z to the power minus 1. Remember, in DTFT, we substituted for z equal to minus 1. And then in, in Z transform, we substituted for z equal to z to the power minus 1. In DTFT, we substituted for e to the power minus j omega. Okay. So here we have to substitute for j omega. Otherwise, it's just a partial problem, partial fraction problem. And we get the answer anyway. Based on this, we get the answer. What is the answer? By the way, the answer is missing here. What will be the answer? So I just observed that the particular slide related to the answer itself is missing. So can we know the answer for this? So C1 is minus 1. Minus 1 divided by 2 plus j omega. 2 divided by, okay, so this is going to be minus 1 divided by j omega plus 2, and this is 2 divided by j omega plus 3. Which template should we use here? This one, where complex exponential e to the power minus 80 gives 1 divided by a plus j omega. E to the power minus 80 into ft gives 1 divided by a plus j omega. Then what was this question here? We had here minus 1 divided by j omega plus 2, or minus 1 divided by 2 plus j omega. So what will be the inverse of this? Anybody? What will be the inverse of this? Minus 1 is a constant. Minus 1 divided by e to the power minus 2t into u of t. And for the second term, 2 divided by 2 multiplied by e to the power minus 3t into u of t. Okay, that will be your answer. Okay, so what did we do here? We did not simply substitute in the expression for the inverse, substitute in the expression for the inverse. Rather, we tried to do this using comparing with the templates. Okay, comparing with the templates. And moreover, you can see we broke the entire problem into two pieces. So that means we used linearity. More or constants in the frequency domain did remain constants in the time domain. So two properties were used. A linearity property was used in two places. Then afterwards, the template, ready answer, was used in another place. Okay. Yes. So then, what is this problem here, by the way? Okay, okay. Yeah, then there is one more interesting problem. So, what was the answer, by the way, for this? What was the answer for this? Did you get the answer for this? So the answer for this is, now see here, this was, as I told you, minus 1 divided by j omega plus 2. This is 2 divided by j omega plus 3. That should give us something like minus 1 into e to the power minus 2t into u of t, okay, plus 2 into minus 1 into 2t into u of t, okay, okay, plus 2 into e to the power minus 3t, minus 3t into u of t, okay, okay. So that was that, okay, that was that, okay. Now, okay, continuing further. Now here this is a problem where there are a lot and lots of properties to be used. So first thing what we'll do here, let us make a list of which all properties might come into picture here. Okay, so this is a problem of finding the inverse. Okay, problem finding the inverse here. So which all properties are coming into picture here? So first thing that you observe here is my omega has been replaced by omega by 3. Okay, so this is one thing, first thing that I want you to observe. Okay, wait. The first thing that I want to observe is my omega has been replaced by omega by 3. hmm, Omega by 3. Second thing that I want you to observe is, okay, this was that the first one. Second thing I want to observe is the entire expression has been multiplied by an exponential in the frequency domain. Okay. Second thing one is multiplication by an exponential in the frequency domain. So this one, omega replaced by omega 3, indicates it's the frequency shift property. No. Which is the property? T into 2, T divided by 3. Omega into 2, omega divided by 3. This is a frequency scaling property. A scaling in the frequency domain has taken place. So we have to see the corresponding property. Second one, your frequency domain has been multiplied by an exponential. So we know this shift in the time domain results in multiplication by an exponential in the frequency domain. Moreover, the third thing that I want you to observe here is the entire thing has been differentiated and multiplied by a j. Okay, so what was that? Multiplication in the differentiation in the frequency domain might result in the multiplication. Differentiation in the frequency domain might result in multiplication by t in the time domain. Okay, so these three properties, along with that, we'll also keep a check on this particular ready template, 1 divided by 1 plus j omega. Okay, so got this thing. So this particular tricky question, it expects you to undergo use three properties. Okay, let us try now. Let us try this problem. Let us see what author has used here. So what does it do, by the way? First of all, he chose this particular thing, 1 divided by 1 plus j omega. Okay, 1 divided by 1 plus j omega has been chosen. Okay, then afterward what has happened? This particular thing Now this omega has been replaced by omega by 3. Okay, omega has been replaced by omega by 3. Which is that property, by the way? Which is that property? Do we know this property? Let us go back. Let us go back. Omega replaced by omega by 3 here, right? So is there any property? Yes, yes, yes. Here you can see. If at all your omega gets replaced by omega by a, given that there is a constant 1 divided by magnitude a, or a in case of just a real quantity, which is missing there, then if at all it is divided in the frequency domain, it is time to multiply it in the time domain. Okay, if at all signal is divided in the frequency domain, it shall be multiplied by the same factor in the time domain, and we should compensate. Now I think this particular a, due to linearity, will come somewhere around here. So our signal is going to be x of omega by 3, right? X of 3t into 3. Okay, shall we go and see that? Shall we go and see that? Okay, so here we are. So what happened? So because of that property, it is x of this particular thing in the time domain. So what was the signal? 1 divided by this was e to the power minus t into u of t. Now what should happen? Since your omega got divided by 3, your t shall be multiplied by 3. Every t shall be replaced by 3t. Every t shall be replaced by 3t. You can see here also t replaced by 3t. Here also t replaced by 3t. And then to make up for that constant, you will also multiply by t. Then author wants to tell that u of t is this particular signal u of 3t. So are you understanding what is if at all x of t? Suppose my x of t was something like this, extending from minus 3 to plus 3. Say this was my x of t. Okay. Then if at all I do x of 3t, what would have happened? X of 3t, what would have happened? The signal minus 3. 3 means 3t. Say x of 3t. Okay. X of 3t, a multiplication. So what does it mean? Scaling factor greater than 1. It compresses the signal. Minus 3 divided by 3 plus 3 divided by 3. So this would be from minus 1 to plus 1. Entire signal would have got compressed. But this you can see, this is u of t. Anyway, it was going from 0 to infinity. So 0 divided by 3, it remained 0 only. And then infinity divided by 3 still remain infinity. So u of 3t will still remain u of t only. So one issue solved. Okay. Divided by omega divided by 3. Scaling in the frequency domain has been taken care by multiplying by the same factor. Okay, 1 by a in the time domain, right? Omega divided by star here, t multiplied by a, it has been taken care. And you can now understand why u of 3t has been replaced by u of t here. Second issue we want to consider is, now this entire thing, okay, this particular thing here, it's being multiplied by an exponential. So multiplication by an exponential in the frequency domain is nothing but shift in the time domain. So multiplied by factor 2, right? Multiplied by factor 2 omega. That means now every t shall be replaced by t by 2. Every t, you can see, every t has been replaced by t by 2. Okay, got this particular thing? Okay, this is the usual shift property. Shift in the time domain is multiplication by exponential in the frequency domain. Now the third thing, differentiation in the frequency domain. Differentiation in the frequency with a z in it. So what is that property? Shall we go and see? What is that property? Differentiation in the z domain should lead us to here. Yes. Differentiation in the frequency. Observe the missing z there, missing j there. Okay. So here is the differentiation in the frequency domain. It results in multiplication by t in the time domain along with the j. Now, since j is already there on the right side, we shall take care by suitably multiplying or dividing. Okay. And there should be a new t introduced. Okay. So did we? Yes, you can see here, since j was already there on the left side, it got cancelled with the right side, and you can see a new t has been introduced in the answer. So there is our answer. Okay. This t is what we introduced now is due to the differentiation in the frequency domain. J did not appear because it was already on this particular side. So which are properties? a time scaling property, then a ready template, then the time shift property, and then finally the differentiation in the frequency domain property. Got it? Got it? So this question, had it been a direct substitution, it would have been a headache. But if it, and moreover in exam, if they explicitly mention that you have to use the properties, then you don't have an option. You have to use the properties. Okay. So now there is one more important question. Okay. So what is this thing here? Author has given x of t and h of t. It's an LTI system. He wants us to find the convolution. Now, since we are in the chapter Fourier transform, I expect that the author is expecting us to use the transform only. So, what is the method, by the way? What is the method? So, this is again, it calls for the convolution property. So, what we will do here is we will do this using the frequency domain approach only. Okay. Now you can see, this is a sync pulse. Okay. How boring this thing is going to be. Okay, so we have solved problems. Okay, first one is also sync pulse, second one is also a sync pulse, and then every sign to be replaced by e to the power j, e to the power minus j, and again this entire thing, if at all I go and try to do this in the time domain, it will be a big headache. Okay, so instead I happen to know that this particular signal happens to be a simple rectangular pulse in the frequency domain. Okay, and my convolution is going to be converted into multiplication. Then taking the inverse of the multiplication would be much easier. So as author intends and as common sense says, I will use the um, which is that property, the convolution property. So what does the property say? First I have to take the x of omega, the Fourier transform of the first signal, then I have to take the Fourier transform of the second signal. First signal, Fourier transform of the second signal, the convolution automatically becomes multiplication. Then I will take the inverse and I shall get y of t. Okay, so now what you have to tell me, okay, what is x of omega? What is x of omega here? You see the question, it is sine pi t divided by pi t. Okay, do not get confused. Sine pi t divided by pi t, and this one is sine 2 pi t divided by pi t. Okay, you got this particular thing. This is not, this is sine pi t divided by pi t. This is sine 2 pi t divided by pi t. So this 2 we have to compensate for 2. So how do we do this? How do we do this? We know what is the template that we are supposed to use here. The time domain, the sync in the time domain. Let us go and see what is that standard result. Is the standard result, sync in the time domain. Okay, now see here we have the standard result, a sync in the sine domain, sine omega t divided by pi t. So sync in the time domain, sine, this pi t does not matter here. Okay, thank God, this does not matter. There we had sine pi t and sine 2 pi t, right? So that was that, sine pi t and sine 2 pi t. Now we will go and use that thing. Okay, so this gave us a rectangular pulse from minus omega to minus w. This is not omega, okay, this is not frequency, this is some constant, minus w to plus w. Now in this place we have pi and 2 pi, right? So now let us cleverly go and substitute this particular ready result, okay, to get the answer of our convenience. So in the first case it turns out to be what is it turns out to see 1 for omega c. So in the first case, so it turned out to be from minus pi to plus pi. Okay, minus pi to plus pi in the first case, minus pi to plus pi in the first case. Okay, that is why this is 1 from minus pi to plus pi. In the second case, it is we had 2 pi, right? So this is minus 2 pi to plus 2 pi. Remember, this is continuous time Fourier transform. This can go from minus infinity to infinity. This is not restricted to minus pi to pi. Okay, this is minus 2 pi to plus 2 pi. Now what happens? The convolution becomes multiplication. The convolution becomes multiplication. So if at all I multiply these two, My answer amplitudes are only one only. Okay, this amplitude is also one, magnitude, amplitude. This is also one. So if at all I multiply these two, I get one from minus pi to pi. Okay, and remaining all places I will get 0. Now what I have to do? Now I have to simply take the inverse. Now I will use the again same template. So sine pi t divided by pi t is my answer. Okay, so cleverly did. Okay, if at all I had to simply try to do it in the time domain, it would be a big headache. Okay, then what else? What other properties we can use? Okay. So here is one more usual suspect here. So I think this is the problem that we solved earlier. Now given directly. So anything tricky here? No. 1 divided by 1 plus 2 plus j omega e to the power minus which one? Which one is which one? Okay, okay, here. So this is a 2, whereas this is a 3. So this one corresponds to 2 into e to the power minus 3t into u of t. This is minus 1 into e to the power minus 2t into u of t. I don't know why author chose to write like this. Anyway, this is in the linearity. Here we have to use linearity property. This is a straightforward question. Yeah. Next one. What is this thing here? Frequency shift property to identify. They have given z of t here. Any big deal? Anything tricky here? Use frequency property to determine Fourier transform of a complex sinusoidal pulse. So author here has mentioned that we have to use the frequency shift property. Okay, that means a shift in the frequency domain implies a multiplication by an exponential in the time domain. That means there is some x of t. There is some x of t which has been multiplied in the time domain. Okay, there is some x of t which has been multiplied by an exponential in the time domain. Okay, whose Fourier transform we have to find? Then we have to then the corresponding multiplication by an exponential time domain should result in the frequency domain. So what may be that signal? What may be the signal? So let us assume that this entire thing is nothing but this multiplied by 1 here. Okay, so let us start with x of t is equal to 1. Let us start with a rectangular pulse which is going from minus pi to plus pi. We will find its Fourier transform. Then afterward, if this thing gets multiplied by an exponential in the time domain, of course, then its Fourier transform will be simple shift in the frequency domain. Okay. Now, shall we? So here it was the ready template. So what is the Fourier transform of rectangular pulse? Fourier transform for rectangular pulse is a sinc. Okay. So using the ready result, Fourier transform for rectangular pulse is a sinc pulse. 2 by omega into sine omega into pi. Okay. So this is again from the ready results. Now shift in the time domain, multiplication by an exponential in the time domain results in every omega to be replaced by, okay, so here every omega should be, okay, can't listen to the voice. What happened? uh, anybody else? So can you not listen to me? Somebody ping me. Your friend is telling that the, okay, maybe some glitch. Okay. So maybe some glitch. I will anyway send you the recording of this also. Yeah. So where were we? So what happened here? Hmm. What happened here? Okay, so we assumed a normal one, a rectangular pulse. Then we assume this rectangular pulse to be multiplied by an exponential in the time domain. Okay, so you see here the plus becomes minus. Okay, in this particular case, I as a student always got confused between this, shift in the time domain, shift in the frequency domain with the sign thing. So that's why every omega shall be replaced by omega minus 10. Every omega shall be replaced by omega minus 10. That's your answer. Then what? Then what? Okay. One more problem. What is this thing? What is this thing? Okay. There is a rectangular pulse, it seems. That's a rectangular pulse, and author wants to use using this result, using the Fourier transform of this x of t and scaling property. Author wants to find the Fourier transform of this particular signal. See here, listen to the question carefully. Now finding Fourier transform of this is very easy. This is nothing but a rectangular pulse in the time domain. But author wants us to get the Fourier transform of this through the Fourier transform this by using the property. Okay, by using the property. So that's why we don't have an option. We have to go for use of property. Okay, so it doesn't mean these kind of questions will be asked here. The author's intention is that we should know how to use the properties. Okay, so let's get started. So what is the relationship between these two? Can you tell me what is the relationship between these two? Okay, this is easy, right? uh, this is a rectangular pulse. We will get a sync pulse. Now we should find out how this x of t and y of t are related. X of t is this thing which exists from -1 to +1. Okay, x of t exists from -1 to +1. Y of t exists from -2 to +2. Okay, y of t exists from -2 to +2. How are they related then? So can I say y of t equal to x of 2t? Can I say y of t equal to x of 2t? No, we cannot do that, right? So because this is the width is increasing, so scaling factor should be less than 1. So it is actually y of t equal to x of t divided by 2. Okay, that is the relation. So now scaling in the time domain, we saw earlier one problem. Scaling in the time domain should result a multiplication by 1 by scaling factor. So your omega gets replaced by omega into 2 along with 1 2 divided by omega. No, nothing like that. So where is this thing, where did this come from? 2 divided by omega anyway was a part of this. Now what happened? Your omega got replaced by 2 omega. Let us see, this is the actual answer. Okay, so let me go back to that property. What does that property say? Here, what is the property? The scaling property. Yeah, what happened? X of t got replaced by x of at. Okay, so there value of a was 1 divided by 2. So what you had to do is your omega should be now multiplied by 2, right? 1 by 8. Omega should be multiplied by 2, and then afterwards the frequency domain, it should be divided by 1 by 2. Again it should be multiplied by 2. Okay, what this particular thing? Now let us go back. What happened here? uh, here. So what happened? Yes, so this explains now the 2 that came from it. Okay, this explains the 2 that came from it. This is also done. Okay, this is also done. Omega divided by 1 by 2, that is 2 omega. I am not now convinced here why this 2 is there. I expected this to be 2 into 2 4. Okay, so somebody run through the textbooks and let me know whether this is correct or not. Okay, this has been clip has been taken from hiking. Okay, just go and see whether this is done correctly or not. Okay, so I wanted this entire thing, but I wanted 2 to be multiplied there. A 2 to be multiplied along with this, so that you would get a 4. Okay, this is fine. This 2 is, just look into it. Okay, okay. Then what other problems are we talking about? This is one straightforward problem here. So what is this? Frequency differentiation property. So what is the property? So e to the power minus 80 into u of t would have given 1 divided by 1 plus j omega multiplication by t in the time domain would have resulted in minus j into the differentiation. Now since there was this j along with omega, this j and j would simply get cancelled and you will get the ready result. Okay. So steps are it's a very trivial problem, I guess, so not necessary. Okay. Now, now, yeah, there is one more. You can see this is a very interesting problem for the kind of setup it has. Okay. What do they ask here? Use the convolution property to find x of t. What is there, by the way? This is a straightforward problem, I think. But since author wants to use convolution property means there should be two convolutions here on the convolution of two variables on the right side here. Okay, in the frequency domain, in the time domain. Okay, or there should be multiplication in the frequency domain, right? What is the convolution property of x of t? Some convolution in the time domain should result in some multiplication in the frequency domain. Okay, so for that to happen, what we should have here, this entire thing should be represented as a multiplication of some two variables. So how do we do this? Sine square is sine omega into sine omega, 4 is 2 into 2, omega square is omega into omega. So there you have it. This entire thing has been replaced by 2 omega, 2 divided omega sine omega into 2 divided omega into sine omega. Okay. So which results in each of these, what are these? Sink in the time domain. Okay. These are sink in the frequency domain, which results in a rectangle in the time domain like these. And we have studied, if at all we convolve this with the same thing. Okay. So okay, so if at all I now discontinue, then I will have, send you the id and password once again. Let me do that. Let me end the meeting here. I will send you the id password quickly.